Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 10 of the course, and in this section we're going to explore a concept called external direct products. And the basic idea, the central idea of this section is how we can take disparate groups, different groups, and piece them together to make larger groups. So that's what we're going to be discussing in this section. So let's go ahead and get into it. This will be section 2.8, external direct products. So we're going to start with just the definition. And I think the definition is very straightforward, and there'll be a lot of, if you've taken linear algebra, you will have seen this kind of thing before, though we didn't refer to it using the same terminology, but it will not be new to you. So this will be the definition. So let's let G1, G2, Gn be a finite collection of groups. Be a finite collection of groups. Okay, so then the external direct product of G1 through Gn is written as, let's write how do we refer to this? Written as, the way we usually notate this is G1 plus G2 plus plus Gn, but instead of the normal plus, we have this plus symbol inside of a circle. So G1 plus G2 plus plus Gn. So this is what we mean by the external direct product. The external direct product of these groups, G1 through Gn, written as this, is the set of all n tuples for which the ith component is an element of Gi, of the group Gi. Okay, and the operation is component-wise. Okay, so this is what we mean by a direct product, an external product, right? So let's put this in symbols. So G1 plus G2 plus plus Gn. Okay, so this is the external direct product. What it is it's an n tuple, G1, G2, Gn, such that Gi, the ith component of this n tuple, is in the group Gi. Okay, and the operations are component-wise, so that means it isn't even necessary that all of the operations of G1 through Gn be the same, right? So think about how we would combine elements. So if I have G1, G2, Gn, some element in this external direct product, and I want to multiply it in this case by G1 prime, G2 prime, Gn prime, another element in this n tuple, or in this external direct product, then the way that the multiplication works is component-wise. So I would have G1, G1 prime, G2, G2 prime, Gn, Gn prime. Okay, and it's understood that for each Gi, Gi prime, the operation is that of Gi. Okay. Right, and so for example, Gj prime, the operation is that of Gj, and those need not be the same, right? This could be, for example, multiplication mod 7. This could be multiplication mod 10, for example. Or this could be addition modulo 3. This could be addition modulo 103. right? So they can be different operations. Okay, basically what you're doing is you're kind of just sort of strapping a bunch of groups together and creating a new group, a larger group. Okay, now this is something, as I said at the onset, we've definitely seen before. Well, I shouldn't say definitely. I mean, if you're taking this class after you've taken linear algebra, you definitely have seen this before. If you're taking this class after you've taken Calculus 3, you may have seen this as well. Probably you did, right? You've seen this in the vector space discussions is the bottom line there. So in linear algebra, we've got this idea of R2, right? And so R2 is what? It's all of the two tuples, right? A, B, such that A and B are real numbers. They're in R, right? You can think of R2 as really just an external direct product of R and R. Same thing for R3. Right, it's A, B, C, such that all three components are in R. And so it's really just R plus R plus R. Right, and then of course Rn, right? Right, so we've seen this before. And really all of that intuition is really what you're going to want to just hang on to. Just keep these common vector spaces in mind as we're going through the examples. I mean, the one thing to be careful of here, of course, is that when we were talking about these as vector spaces, we have this idea of scalar multiplication, which doesn't really enter into the discussion at this point. So just kind of forget about that piece of it and think of these as external direct products with this operation of component addition, right? So ignore scalar multiplication for now. We don't have anything like that in external direct products of groups. But I think the intuition of component-wise operations and closure and all that jazz, that all can be brought into this way of thinking. Let's see some examples. And I guess we did just see a couple examples. Let's see some more abstract algebra type of examples. Okay, let's consider U8 and U10. Okay, now U8, remember, is the elements 1, 3, 5, and 7. And U10 was 1, 3, 7, and 9. And remember, these are the multiplicative groups, modulo 8 in the case of U8, and modulo 10 in the case of U10. Okay, and we can create an external direct product of these groups. So U8 plus U10. What does that look like? Well, for each of the elements in this group U8, U10, the first component is going to be from U8. Second component is going to be from U10. Right? So we could just kind of write these all out. Right? So we can go like this, 1, 1, 1, 1. So we know that this is going to be the first component of 4 elements. And then 3 is going to be the first component of another 4 elements. And then 5 will be the first component of another 4 elements. And so if you're writing these out, you can kind of adopt that strategy. You know, write out the first components first and just use the appropriate amount of repetition. And then you can just fill in the other ones. Right, and so this would be, so the second component is going to be 1, 3, 7, and 9. Just like this. Right, so this is the external direct product of U8 and U10. And so it's a group with 4, 8, 12, 16 elements in it. Now, if I want to take 2 elements inside of this external direct product and I want to combine them, let's say 3, 7 and 7, 9. Then for the first component, the 3 and the 7, I need to use the operation of U8. And for the second components, the 7 and the 9, I need to use the operation of U10. Right? Both are multiplication, but they're multiplication with different modulo. Right? So let's do the multiplication. So this would be 3 times 7 mod 8, and then it's 7 times 9 mod 10. So this is 21 mod 8. Obviously, I'm kind of filling in a lot of the gaps here to make sure this is really clear. And then it's 63 mod 10. All right, and so 21 mod 8 is, well, you've got 16, so 21 minus 16 is 5. And then 63 mod 10 is obviously 3. Right? So the two would combine like that. Now, the key thing here is that this first component is the operation of U8, and the second component is the operation of U10. Okay. Hopefully that's straightforward. This is a pretty simple kind of example to look at. Hopefully that's straightforward. Good. What about, let's do another example. How about, what about Z2 and Z3? Another kind of simple example. Z2 is the integers modulo 2, so you've got 0 and 1 in there. And then Z3 is the integers mod 3, so that's 0, 1, and 2. And so if I want to combine those, well, I'm going to have 3 elements that start with 0 and then 3 elements that start with 1. Right, and then the elements are going to be 0, 1, and 2. 0, 1, and 2. 0, 1, and 2. Okay, so that's my external direct product of Z2 and Z3. Now, if I want to combine these elements, right, if I take 2 elements in here, maybe I'll take 0, 2, and 1, 1. Remember, the operation here is addition for both groups, so you can write it like this if you like. Otherwise, you could write it the other way if it's clearer, but I would think this would be clearer. And so you're going to have 0 plus 1, and remember that's mod 2, and then 2 plus 1. Now, it's not necessary that you write mod 2, mod 3 like this. Like, I'm just doing this so that it's clear what I'm doing. But in practice, you don't have to write it like this. You could just do the operation, keep track of it in your head. Right? But this would be 1 mod 2, and this would be, of course, 3 mod 3. And so this would simplify down to 1, comma 0. Right, now again, just keep in mind that the first component is mod 2 addition. The second component is mod 3. Right, so different operations. Both addition, but with different modulo. All right. Now, a couple of things to notice about external direct products, and some of this we'll get into in more detail later, but just things to point out. Now, in the case of Z2, Z3, well, in the case of Z2 and separately Z3, these are both abelian groups, right? Meaning that the operation commutes for every element in the group, right? So 0 plus 1 is the same as 1 plus 0, and the same thing is true in Z3, right? So they're both abelian. So Z2 and Z3 are both abelian. So that means Z2 plus Z3 is also abelian. Right, so the external direct product will naturally get that commutativity from the component groups. Okay. So another thing to know, so that's kind of the obvious thing, right? I mean, I suppose that's pretty obvious. Hopefully it is, right? Because I mean, if the first component commutes, and second component commutes, then the whole thing commutes, right? So that's hopefully clear. The second thing to think about here is let's talk a little bit about the order of these groups. So like if we look at Z2 plus Z3, the order we see of course that there's 1, 2, 3, 4, 5, 6. The order of Z2, Z3 is 6. And it begs the question, how does this group relate to Z6? How does this relate to the other integer modulo n group Z6? How does this relate to Z6? Okay, let's talk about that. And this is something we'll bring up later, but let's consider the element 1, 1 that is in the direct product Z2, Z3. Okay. All right, so we know 1, 1 is in that direct product. We just saw it, right? Just look at the elements. It's what the third or fourth element that we listed. It's fourth element, I think. Okay. Let's see what we can generate with 1, 1. Right? So let's think of 1, 1. It's an element in a group. Let's think of the group that we can generate from it. Okay, so first of all, 1 times 1, 1 is just 1, 1. Okay. What about 2 times 1, 1? Well, that gives us 2, 2. And 2, so remember the first component is mod 2, the second component is mod 3. So this is actually 0, 2, isn't it? Okay. Right, so what about 3 times 1, 1? And the reason I'm multiplying here, it's really 1, 1 plus 1, 1 plus 1, 1, right? But I'm just saying 3 times just for brevity, right? This is just 1, 1. This is 1, 1 plus 1, 1. This is 1, 1 plus 1, 1 plus 1, 1. So I'm just doing 1, 2, 3. Okay, hopefully that's not throwing you. This is really, we're just using the cyclic group generator here, right? And so this is 3, 3. Right, which we can think of as 3 mod 2 is 1 and 3 mod 3 is 0. Okay, so we've got these 3 elements so far. What about 4? Well, that's obviously 4, 4, which is what? Well, 4 mod 2 is 0 and 4 mod 3 is 1. And then 5, 1, 1. That's 5, 5. And that is going to be 5 mod 2 is 1, and 5 mod 3 is 2. What about 6? Well, 6 mod 2 is 0, and 6 mod 3 is also 0. Right, so something to notice here is that, so what we can see here is that the element 1, 1 generates the whole group. It generates the whole group, right? So that implies what? So if you have an element in a group that can generate the whole group, then that implies that Z2, Z3 is a cyclic group, right? And if Z2, Z3 is a cyclic group of order 6, that implies that Z2, Z3 is isomorphic to Z6, which basically means that these two groups are the same, they just look different, right? They have the same number of elements, they all act the same way, right? And so they just look different. Okay. Now, so that's very interesting, right? You've got a external direct product of Z2 and Z3 happens to be isomorphic to Z6, right? 2 times 3 is 6. So you may be impelled to believe that Zm plus Zn is going to be isomorphic to Zm times n, right? You may want to believe this, but note, it is not always true. This is not always true. In this case, it's true. Z2, Z3, the external direct product, is isomorphic to Z6, But it's not always the case. And we'll see in a couple of minutes, when this fails, when this works, and it's actually quite fascinating. Okay, we'll see when this works. This is not necessarily always true. And you could easily prove this to yourself. You could find a counterexample. If you look at so a counterexample that is easy to work with is z2 plus z2, right? And we know that that's 0, 0, 0, 1, 1, 0, and 1, 1. And that is not isomorphic. So z2, z2, you might think it's isomorphic to z4, but it is not. Right? And the reason it's not, I mean, one way you could see it is that we know Z4 is a cyclic group, but if you go and you look, try to find a generator in here for Z2, Z2, you're not going to find it. You're not going to find it. So try to find a generator. And you will not find it. Z2, Z2 is not cyclic. I invite you to try it, though. It is a good exercise to try it. It's just one way to see that the two are not isomorphic, right? Obviously, if this is a cyclic group and this is not a cyclic group, they can't be isomorphic to one another. Okay. All right. Very good. Very good. Okay. So the next up, we want to look at a theorem. Okay. And this is going to be a theorem that, so we're kind of moving into some of the properties of external direct products as groups. Thinking of them as groups, what are some of the properties of them? So one of the things that you might wonder about is, if these are groups, sure, okay, I can buy that. How do we know what the order of an individual element inside of a group like this happens to be, right? Because the elements are kind of strange, right? They're like these tuples. So how do I know what the order of an element is? And that's what the next theorem is going to address. So the order of an element in a direct product, order of an element in a direct product, and it's a direct product of a finite number of finite groups. I'm just going to leave it like this. The order of an element in a direct product is the least common multiple it's the least common multiple of what? Of the orders of the components of the element. Right? That's exactly what you would expect and hope for, actually, and it's the case, right? So if I have some element G1, G2, Gn, which is an element of an external direct product, and I want to know the order of it, right? So the order. Then what this theorem says is that the order can be found by identifying the least common multiple of each of the components, the order of each of the components. So the order of G1 and the order of G2 and the order of Gn, right? Whatever the orders of each of these happen to be, find the least common multiple, and that's the order of the overall element. Perfect, right? Perfect. Okay. So let's see an example. Let's say we've got Z25 and Z5 external direct product here. Let's say we want to know what is the order of, and we'll say, let's see, how about 5 and 0? Well, let's say 10 and 0. Okay, so 10 is an element of Z25, 0 is an element of Z5 in this case. Okay, so the order of 10 comma 0 is equal to the least common multiple of the order of 10 and the order of 0. So what are the orders of these values? So let's start with 10. So 10, obviously the order is greater than 1, so 10 plus 10 is 20. Okay, that's not equal to 0 mod 25. Plus 10 is 30, not equal to 0 mod 25. Plus 10 is 40, not equal to 0 mod 25. Plus 10 is 50, which is equal to 0. Right, so the order of 10 is 5. Okay, what about the order of 0? Well, 0 is the identity element in Z5, so the order is 1. And so the order of 10 comma 0 in this external direct product must be the least common multiple of 5 and 1, which is 5. Right? So the order of 10 comma 0 is 5. Okay, it's the least common multiple of these two individual component elements from the disparate groups. Okay. All right. What about, and this will be another contrived example, what about how about 15 comma 4? Well, the order of 15 comma 4 it's going to be the least common multiple of the order of 15 and the order of 4. All right, what is the order of 15? Let's figure that one out first. So remember, this is in Z25. So we've got 15 plus 15, that's 30. Plus 15 is 45. Plus 15 is 60. Still not 0 mod 25. Plus 15 is 75, which is 0 mod 25. Right, so that implies that the order of 15 is 5 again. 1, 2, 3, 4, 5. Okay. That's great. What about the order of 4 in Z5? Is it Z5? Yep. Right, so I've got 4 plus 4, which is 8, which is not congruent to 0 mod 5. Plus 4 is 16. That would be what? 1 mod 5. Plus 4 is 20, which is congruent to, let's see, 16. 4, 8, 12, 16, which is not congruent to 0 mod 5. Plus 4 is 20, right? So this is 20, which is congruent to 0 mod 5. Mod 5. Okay. So remember, we're in Z5. 4 is congruent. 4 plus 4 plus 4 plus 4 plus 4 is 20, which is congruent to 0 mod 5. So that means the order of 4 is equal to 5. Okay. And so the order of the overall element, 15 comma 4, is equal to the least common multiple of the order of 15, the order of 4, which is the least common multiple of 5 and 5, so obviously the order is 5 again. Okay. Perfect. All right, so pretty straightforward. All right, let's look next at, let's do another example related to this. Let's consider Z30 and Z12. Okay. The element, let's consider an element from each. So first we'll start with 5. It's an element of Z30. And the order of 5 is 6. Okay. And then let's think about 3 from Z12. The order of 3 in Z12 is 4, right? So you could go through and confirm this, right? These are straightforward, simple examples, but similar to what we did in the previous example, you could confirm that the order of 5 is 6, and the order of 3 is 4, right? And so the order of 5, 3 would naturally be 24, right? The product of those two. In this case, the least common multiple would be the product. Okay, and so we can actually, for this example, I want to do is I want to actually specify something different. Let's think about the subgroup generated by these two elements in each case, right? So the subgroup generated by 5, we know that's 0, 5, 10, 15, 20, and 25. This is a subgroup of Z30, remember? Okay, and then 3, the subgroup would be 0, 3, 6, and 9. That's a subgroup of Z12. Right, confirm that this is indeed, these are indeed the subgroups. Right, these are subgroups of this. Right, and so what we can actually do is we can think of these two as creating a subgroup inside of the external direct product. Right, so 5, the external direct product of the subgroup generated by 5 and by 3 is going to be a subgroup of the external direct product of Z30 and Z12. Okay, right? This is a subgroup. Okay, it's a subgroup. Right, what's the order of the subgroup going to be? How many elements are going to be in the subgroup? Well, this one has got what, 6, 1, 2, 3, 4, 5, 6, and 3 has 4, and so an external direct product of 6 elements and 4 elements is going to necessarily give you 24 elements, isn't it? Okay. Right, so this notation is really helpful when talking about subgroups of external direct products. It can make, thinking about these things and notating them much more straightforward. Okay, very good, very good. Let's keep moving. Let's move forward. Okay, we got another theorem here, and this is one that I mentioned earlier that would be coming. This one and the following. So let's let G and H be finite cyclic groups. Right, finite cyclic groups. Then the external direct product of G and H is cyclic if and only if the order of G and the order of H are relatively prime. What does relatively prime mean? Let's just make sure we remember that. Relatively prime means that the only common divisors of the two groups are 1, of the two numbers are 1. So for example, 2 and 3 are relatively prime. The only thing that divides the two is the number 1. 11 and 3 are relatively prime. Okay. All right. So this is saying that if you start with two cyclic groups, right, G and H, if you start with two cyclic groups, G and H, and you combine them as an external direct product, then the external direct product you get is cyclic if and only if the two groups that went into it are relatively prime in order. Okay, so that's kind of interesting. That's something that you might not have expected. Right? And so this goes back to our previous example of Z2 and Z3. Right? Z2 and Z3 we know are cyclic groups, but we said that, and then we said that Z2, Z3 composed as an external direct product was also cyclic, and that's because the 2 and the 3 are relatively prime. We also saw that Z2 and Z2 compose, when we compose those as an external direct product, they do not yield a cyclic group. And that's because the 2 and the 2 obviously are not relatively prime. They have a common divisor of 2. Right, and so what we saw, Z2 plus Z3 is cyclic. Z2 plus Z2 not cyclic, right? And that's because 2, 3 are relatively prime. And here obviously 2 and 2 are not relatively prime, RP. Okay, so that was the idea. All right, so let's prove this theorem. Let's prove this one. It's a pretty straightforward proof. I mean, it's a little tricky, like algebra proofs can be, but it's not. There's nothing in it that's too difficult. Let's start by let's let the order of G be M, and the order of H be N, and so that means the order of the external direct product must be the product of those two numbers, right? Okay, M times N. Okay, so we'll start with that, and now let's prove the one direction. Okay, so we'll start by assuming that G and H are cyclic. G and H external direct product is cyclic. Okay, and so given that assumption, what we want to show is that M and N, these two, must be relatively prime. We wish to show that M and N are relatively prime. Okay, so let's go ahead and assume the greatest common divisor of M and N is equal to some number D. And because G and H is cyclic, it's going to have a generator. And let's let G comma H be a generator of GH, the external direct product. Right, we know that because it's cyclic, it must have a generator. And so we'll let GH be such a generator. Okay. Then what we can do is we can consider the element G comma H in G and H, and let's raise it to a very specific power, Mn over D. So Mn is the order of the group, and D is the greatest common divisor. Right? Now what happens here? Well, what ends up happening is that you can break this apart in a clever way. So G to the M and then to the ND. Right? M is obviously the order of group G. And H, we're going to do similar. We're going to do H to the N and then to the M over D. Right? Now what happens if I raise, well, remember G is the generator in G, H is the generator in H, so G to the M is going to be equal to the identity, and H to the N is going to be equal to the identity. So this is E to the N over D, and then E to the M over D, which of course the power doesn't make any difference now, so it's E. So it's the identity element in the external direct product. Okay, and so what does that mean? Well, it means that M times N, this all implies that M times N is equal to the order of the element G comma H. Okay, and of course the order of G comma H is going to be equal to, less than or equal to M times N over D. But in this case, if I divide M times N by anything other than 1, I got a contradiction. Right, so this is going to imply that D is equal to 1. And D is the GCD, remember. of m and n. Right? And so that's how you get it. You can see, if this being the case, if I start with the assumption that G and H is cyclic, then that implies that the order of the two groups must be relatively prime. Okay, that's what we wanted to show. Okay, so that was the one direction. Let's do the other direction now. Right, in the other direction, we want to start with the idea that the orders are relatively prime, right? So we'll assume that there's a little g that generates g and a little h that generates h. And of course, we're assuming the order of g is equal to m, and the order of h is equal to n, and the greatest common divisor of m and n is equal to 1. Right? So we're assuming all of that. Okay. All right. So we've got the generator of g is g, the generator of h is h. So again, let's consider gh as an element in the external direct product. Like so, right? Right. So let's consider, what is the order of this element? What's the order of the element gh? Well, we know that the order is equal to the least common multiple of the order of each of these guys here, which it's equal to the least common multiple of m and n. Right? The order of g must be m because it generates g. The order of h must be n because it generates h, right? Okay. So the least common multiple, well, we assume that these two are relatively prime, so the least common multiple is mn. Okay. And that, of course, is equal to the order of the external direct product. Right? And so what does that imply? Well, it implies that this is a generator of the whole group. It's a generator of the external direct product. And so that implies, of course, so therefore G plus H is cyclic. Okay, so it's a cyclic group. Right, if we have relatively prime orders, then we naturally get a cyclic group. That's the bottom line there. And so that's both directions, of course, and that is the proof. Okay, so that is the proof that tells you when you have a cyclic external direct product. Right, and this was just an example with two groups, G and H. This can naturally be extended to however many groups you like as an external direct product. So an external direct product, we'll say G1, G2, Gn. Okay, external direct product of n groups. And I'll specifically say of a finite, it's got to be a finite number of cyclic groups is cyclic. Right? An external direct product of a finite number of cyclic groups is cyclic if and only if, in this case, G of I, the order of G of I, and the order of G of J are relatively prime when I is not equal to J. Okay, so it's the same idea. It's just that obviously the number of numbers you have to check increases as the number of groups in the external direct product increases. Okay. Very good. All right. So that's the that theorem. Now a closely allied theorem is what we'll end on for this section. And so what the last theorem that we'll look at is a pretty beautiful result, actually. What it says is that let's let if we let m equal n1 times n2 times ... nk, right? So if you've got some number m, which is a product of k other numbers, then z sub m, okay, the integers mod m, is isomorphic to zn1, zn2, znk, right? So I've got zm, which is isomorphic to the external direct product of zn1, zn2, znk, and that they're isomorphic if and only if ni and nj are relatively prime. When I is not equal to j. So it's a direct, really you could think of it almost as an extension of the previous theorem. Okay, right? And so this is the other piece of the, what was it? Z2, Z3 is isomorphic to Z6, right? So we saw earlier that Z2, Z3, external direct product, was isomorphic to Z6. And now we see why that is. It is the case because 2 and 3 are relatively prime, so we can combine them to get something that looks a lot like Z6. Okay. Now it turns out that you can kind of use this criteria for isomorphism to express really the same group up to isomorphism in many different ways. Here's a great way to look at it. So if I have Z2, direct product of Z2, Z2, Z3, and Z5, for example. Okay, if I have those 4 groups, well, I can look, for example, these 2 are relatively prime. So I could combine them. So Z2, Z3, external direct product, is relatively prime to Z6, as we saw here. So this whole group would be isomorphic to Z2 plus Z6 plus Z5, right? So this piece here, that's isomorphic, right? Obviously, this Z2 and Z2 are isomorphic to the same. Z5 and Z5 are isomorphic, and this middle section would be isomorphic to this component. So remember, this is a 4-tuple. A1, A2, A3, A4, and it's going to be isomorphic to a 3-tuple. Right, now in particular, the 2 and the 3 here are going to combine in such a way to give you an isomorphism with that second component. Right, and you could go further. You could write, well, maybe I want to combine these two. 6 and 5 are relatively prime, so I could combine those, and I would have Z2 plus Z30. Right, so here I've taken a 3-tuple and I've compressed it down into an ordered pair. Right, so these 2 here would be isomorphic to the Z30 part. Right. Now, similarly, we could do something kind of similar here. Let's say I start with my Z2, Z2, Z3, Z5. Well, one of the things that I could do is I could change the order of these if I wanted to. Right? I could rewrite this in a different order. Okay, I could do it like this. I could go Z2. So the Z2 and the Z2 next to each other would be problematic because they are not relatively prime. But if I wanted to combine these 2 and these 2, I could I could change the order and write Z2, Z3, Z2, Z5. Right? So I just kind of took these 2 and interchanged them. You can think of it that way. And now these 2 are relatively prime, and so are those 2. right? And so I could re-express this as Z6, and I could re-express this as Z10. Okay. Right. No, so notice that I started with the same group here in both cases, and I arrived at these different isomorphisms. So what this is saying is that Z2, Z30 is isomorphic to Z6, Z10. Okay. Right. Right. So this is true. This is true just because of what we just derived here. Right. Because of this theorem that tells us when when an external direct product is equivalent to the integers mod m. It tells us when we have an isomorphism, and so I can derive this. Right. That these seemingly very distinct ordered pairs would actually be isomorphic to one another. Right. Now notice, and this is important, right, Z2 plus Z30, you may want to say this is true. You may want to think that this is isomorphic to Z60, right? But it's not, right? Because you don't have relative primeness of these two, right? 2 and 30 are not relatively prime, right? So this is not true. And the reason it's not true is because 2 and 30 are not relatively prime. Okay. All right. So that's where we're going to end this section. So again, this is there's lots more that could be said on this stuff. We have to move forward. So this section was all about how do we take different groups and combine them to form kind of think of them as composite groups, external direct products. The next section is going to be kind of the reverse. How do we take a group and factor it down? Right. So in the next section, we'll get into factor groups, and we'll also talk about normal subgroups. That's kind of a connection there. Right. So next time we'll get into normal subgroups and factor groups. All right. Until then, take care, and we'll talk to you all next time.